Ever wondered how AI makes sense of networks that never stop changing? Think social media trends, traffic patterns, or disease spread. These are dynamic graphs, where connections between people, places, or ideas shift over time. But here's the problem. Traditional methods for simplifying networks are like freezing a moving movie into a single frame. They work for static snapshots, but when time is involved, they fall apart. Why does this matter? Dynamic graphs aren't just big, they're complex. They have layers of time-dependent relationships, and shrinking them without losing that temporal DNA is like condensing a 3D movie into a still image without losing the plot. It's not just about size, it's about preserving the story. Enter DyGC, a breakthrough framework rewriting the rules. DyGC doesn't just shrink graphs, it preserves their evolving essence. How? By borrowing a trick from biology. Imagine your brain's neurons firing in patterns to process information. DyGC uses a spiking structure generation mechanism, mimicking how neurons transmit signals over time. This lets it model how connections in a dynamic graph change, like a dance where each step depends on the last. It's not just about structure, it's about timing. But here's the real magic. DyGC aligns the distribution of data across time. Think of it as matching the rhythm of a song. Each snapshot of the graph must sync with the overall tempo. This ensures the condensed graph isn't just a random sample, but a faithful replica of the original's time-based behavior. The results? Mind-blowing. DyGC achieves 96.2% of the original model's performance while using just 0.5% of the data, and speeds up training by 1,846 times. It's like taking a blockbuster movie and condensing it into a trailer that still captures the plot, action, and emotion. Let's break it down. Traditional methods struggle with dynamic graphs because they're built for static snapshots. Imagine a traffic prediction model that loses track of rush hour patterns because it's too busy counting cars. DyGC solves this by focusing on two things. 1. Structure, keeping the core connections that define the network. 2. Evolution, making sure the simplified graph still shows how those connections shift. So how does DyGC do this? It uses a clever combo of machine learning and math. Think of it as training a graph architect that learns to build simplified versions of networks. This architect isn't guessing, it's guided by two rules. Distribution alignment, ensuring the condensed graph looks statistically similar to the original. Logit alignment, making sure the simplified graph behaves the same way in AI models. It's like summarizing a TV series. You don't just pick random scenes, you keep the plot, character arcs, and key moments. DyGC does the same for graphs, preserving their story even when they're smaller. But here's the catch. Dynamic graphs have sudden changes, like a road closing at noon or a viral post exploding. These non-differentiable moments are tricky for math models. DyGC tackles this with a surrogate gradient trick. Think of it as a mathematical workaround that lets the system learn from abrupt shifts without breaking. So next time you see a complex system evolving, whether it's a social network or a medical dataset, remember, tools like DyGC are making sense of it all. Because in a world where everything changes, understanding the why behind the change is the real breakthrough. Thanks for watching. If you want to dive deeper into how AI tackles dynamic systems, hit subscribe. The future of data science is evolving, and we're just getting started.